Good morning. This is Dr. Liebovitch, and this is lecture 4A. So this is apparently one of the A lectures as opposed to one of the B lectures. What we're going to do, I've handed out the homework for next time, and I'm going to go over the homework from the previous time a little bit. And everyone should sign the attendance sheet, which is floating around, or is probably stationary rather than floating at some point. And if everyone has signed that, that would be very nice. And I also have an announcement that we're not going to meet next time. I mean, we're not going to meet next week. There will be a next time. So next time is actually 2 weeks from today. So that's when next time is. And there'll be no class next Friday, because I'll be in Israel. It would be a long commute. Okay. The next homework is self-explanatory. I won't say anything about it. Let's go over a little bit of the previous homework, because there's some aspects of it that are not so self-evident. And let me show you what the difficulty is in the homework. So if we could switch to the Elmo. Thank you. This is sort of the typical problem that we had last year, where nobody in the class got this problem right, or 2 years ago. But it looks like some people have gotten it right this time. This is an example of a person who did not get the problem right, whose identity we're keeping protected. So here we have the data, which is probably done very accurately. And we have the fit of the Gaussian, which is done, alleged Gaussian, which is done very accurately. But you can see that this Gaussian doesn't really seem to go through the data points. And if you remember, I said the whole unusual thing about using the mean and variance to fit this data was that we didn't have to do a least squares or any other fit, that we could just from the mean and variance have the Gaussian automatically fit through the data. And you can see here the Gaussian is not running through the data. So I'm going to go over why this happens in ways that this can be fixed. And we'll see this has to do with how we normalize things in the data compared to the theory. And in some ways, it's easier to look at histograms in terms of the data and a probability density function, which is probably what's drawn here, in terms of the theory, or vice versa. So it's easier to plot this as PDF and more difficult to plot this one. And we really need to plot them both in the same form in order to compare them. So I'm going to go over that, because that was a point that apparently is obvious to me but wasn't obvious to anyone last year. You can see, on the other hand, that in this plot from another person, that in this case the Gaussian does go through all of the points of the data, and we'll see how to do this. The other reason why I wanted to show you these was to look a little bit at the distributions of the paint smears or ink smears that people had. So first of all, let me show you the very beautiful smears that some people had. Some really nice ones. No, they were all nice, actually. Do I have mine here? Mine are a little uglier. But so this is one set, and I'll show you another set. Here. This shows another set. One of the things you might be looking for in terms of this data, many of these paint smears, and certainly the one that I did, usually have a few big ones and then lots more smaller ones. You can see these red circles encompass a lot more smaller ones, and there are a lot smaller ones than real big ones. There are a few really big ones, but most of them tend to be somewhat smaller. And that's sort of typical of data that's produced this way. We can see it, I think, maybe even more dramatically in this one, where again we have a few big ones, maybe about 20 big ones, and maybe a couple of hundred small ones. And we can see it again here in color in this one, where we have, again, a few big ones. This one looks like the biggest. Maybe this one is the biggest. And then as we go to smaller ones, a few medium-sized ones and lots of smaller ones. And I guess those are all the ones that I have here. And let me show you what mine looks like. Skipping ahead here. This is exciting. This is a little hard to see, but this is what mine looks like. So I have one big one and lots of small ones. You can see the small ones there. And I did the measurements on these. And the point of this, and I'll show you mine and we can go over some of the other ones later. This is the probability density function, or the histogram, that I calculated from my data. And what's plotted here is the logarithm of how often I saw things against the size of the things at which I saw. So this is a plot of logarithm versus logarithm. And you can see that this is almost a straight line. And it has a slope of, in my case, about 1.34. So the number of points of a certain radius is proportional to r, the radius to the 1.34 power. And the reason for doing this is that in this course so far we've emphasized Gaussian distributions. And we've emphasized the reason why we think we have Gaussians. Because when we do a measurement, there are lots of little errors involved in making the measurement. And some of those errors push things up and some push down. And if we have a large number of small independent errors, then we'll get a Gaussian. And the point of doing this exercise is to show you that, in fact, in nature, that's not the case at all, most of the time. Most of the time in nature, we have many small things, a smaller number of bigger things, and very infrequently a few really big things. And that very often we have distributions like this that are a straight line on a power law and are not at all Gaussian. And as we'll see later, the moments of these distributions, like the mean and the variance, do not exist. And these cannot be evaluated by the sort of Gaussian statistics that we're used to, and cannot be characterized by means and variances. Yeah?
Doesn't somebody's name become associated with this principle?
There are lots of different names associated with this principle. We can call this a power law distribution. We can call it a Liebovitch stable distribution, spelled L-E-V-E-Y, with an accent, which I think is probably a grave accent, so it's probably the other kind. So this was a French mathematician, Liebovitch, who lived, is this a grave accent, or what's the name for this accent? Because there are two, right? There's one like this, which is this. What?
I think that's an acute.
An acute, okay. And this is grave? Is this grave? Okay. There's a reason why I got C in French. Liebovitch in the 1920s did a lot of work on this. His work has never been fully published into English. There's a book he published in the 1920s that describes this. I would call this distribution fractal or power law. And we'll see that these cannot be characterized by moments. The moments don't exist. The simplest way of understanding why the moments don't exist is if we look at someone's data that looks a little cleaner than mine. This is nice data. The reason why the moments don't exist, if I start taking the average, and as I have a small amount of data, the average will be dominated either by the few big ones or the large number of small ones. And as I accumulate more data, either I'll pick up so many small ones that the average will keep getting lower and lower, or I pick up every once in a while a big one, which biases the average to be much bigger. So the average I get will change with the amount of data and will keep getting lower and lower, or larger and larger, depending on the properties of the data. And so there's no average. That is, in the Gaussian distributions that we're used to using, if I plot and I can call these the sample means, meaning I take them from the data, for a Gaussian this may fluctuate but reaches a finite limiting value that we identify as what we call the population mean. So the population is kind of like the real one. But for these fractals, as I say, well, in either two regimes, either these numbers keep growing forever or the numbers tend towards 0. So in this case, we have no means, and we can't characterize the data by a mean. In fact, if you think about this, this should really be shocking to you because you're so used to taking experimental data and finding the mean in the experimental data that it should be really disturbing to you that all of a sudden, that we can't do that, that it has no value or no meaning in the mean. One of the talks I'll be giving while I'm away, which I gave here last December, is called When the Mean is Meaningless, examples from mathematics and cardiology. And we have a lot of real data which has these properties. And what I wanted to do is to give you an example of analyzing your own data to see that a very simple system can produce properties like that. And this shows some examples from one of the people. And again, this is a probability density function. This is linear. And from what I was saying a couple times ago, maybe even last time, was that very often we want to plot functional relationships on different types of axes to better show what they look like, because this just looks curved and we can't tell what the functional form is. But here, this plot is now on a log-log plot, and we can see, although the data is limited, that there looks like to be something like a power law relationship here. That is a straight line on a log-log plot, which means this is an example of fractal scaling. But not everybody found that. So, and data can be genuinely different. This plot actually looks as if it has this is not from that. This is from that. So here it looks like there's a peak and then a tail again. So this one did not have that characteristic. And let's see if we can find another one here. This one kind of looks Gaussian if you look at it first, but if you look at it a little more carefully, there's really this very long tail, which is stretching on for quite a bit. And this tail, I would imagine, if plotted on a power law plot, might have a straight line characteristic. So we're really talking about this high tail. If this was a Gaussian, it would be tail off here or trail off here, and we wouldn't see anything. And you can see there's still a lot of additional data. Every once in a while, there's a really big splotch. So the purpose of doing this exercise was to show you that even under relatively normal circumstances, we can get these distributions which have properties that are completely opposite or different than what they told you in your other statistics course. Okay? So this is like real statistics. And also to show you that different people have different results in the data. That not all distributions are fractal, and they can be partially fractal, or they can have Gaussian properties, to show you that there's really a range of different possible distributions that people have. So nobody ever gets this thing wrong, this exercise wrong. People can generate different types of distributions. Okay, so that's the overall background on the homework. Let me go through some of the details of the homework and sort of try to make it clear how we can resolve this issue of getting that Gaussian curve to fit the histogram in the data. So the basic issue here is that in looking at data, the easiest way to handle the data is by using these histograms. But the easiest way to handle the theoretical fits is by using the probability density function. And these two things, although they're related, are not exactly the same thing. And what we need to do is we need to plot them in ways that are equivalent so that we can see how they fit. So that means from the data, we either have to generate the PDF, or from the theory, we have to generate the histogram. And then once we have that, Then we can compare the histogram from the data to the histogram from the fit. We can compare the PDF from the theory to the PDF from the data, and that will allow us to fit things. So I'll do this from the beginning. It looks like people have made pretty nice histograms. So for example, in making the histogram from the data, we have some axis, and we might say that a good bin size might be 5 units, for example, just from the way this data is. So we might look at how many times we have numbers between 50 and 54, and 55 and 59, et cetera. And I think everybody, just about everybody, did this. Now, one issue in how do we choose these boundaries? And the answer is, we can say trial and error. We want to choose them big enough to include enough data points, but not so big that we lose resolution. So you just pick what seems reasonable. We want a few points in each bin, because if we pick the bins too narrow, then some of them may have 0 points in them. And if we pick them too wide, then we're going to be losing resolution. Now, one of the interesting issues that comes up is how are we going to plot these on the axes. So for example, this bin, if this is 49, 48, 50, 51, 52, 53, 54, 55, etc. One way to plot this bin, since this is between 50 and 54, might be to plot it from 49.5 to 54.5. Because we don't know, in this case everything is an integer, but we'd like the bin centered on where the values are. So this is everything between 50 and 54. And the next bin, apparently the next bins are blue on either side, blue bins. So, you know, if we just plotted it from 50 to 54 and the next one from 55 on, then we're going to kind of create gaps here. We don't really want gaps. So you have to think a little bit about where the boundaries of the bins are. And if we have integers and include 50 to 54 inclusively, then maybe 49.5 to 54.5 might be where we want to plot the bins. Say this in a different way. This means that the center of the bin is going to be at 52. So this is 1, 2.5 units, 1, 2.5 units. So that means that the centers of these bins that we've plotted are going to be at 52, 57, 62, 67, etc. You can make this European bins. Okay. All right, so now let's see how we're going to compare this to a Gaussian. The Gaussian probability density function, Gaussian, is f of z equals 1 over the square root of 2 pi e to the minus z squared over 2, where z equals x minus m, the mean, divided by sigma. So what we want to do in the fit, if we're trying, so let me see what we're trying to do here. Okay. What we're trying to do here is to convert this PDF that we have from the Gaussian to a histogram. Okay. So what we need to do is, given the range of where the bin is, let's say the bin is over here in the data, so this is going to be 49.5 to 54.5, correspond to that. What we need to do is to integrate the probability under here to find out how much the probability there is, because the number of events will be equal to this probability, which I'll call P 49.5 to 54.5 times the total number of events. And if we have that information, then we can plot that as a histogram. So what we need is to generate this P. And there are a number of different ways we can do this. So I'll show you how to do that in a couple of different ways. One way to do it, and this is a popular way in spreadsheets like Microsoft Excel, has a function, capital P of x equals the integral from -∞ up to x of the probability density function. X equals, from z equals -∞ to x. So what that is, let me draw it cleanly. So if I have the integral from -∞ up to, for example, 3, and I have the integral from -∞ up to 5, if I'm really looking, trying to find the area between 3 and 5, the way I can do it is the probability between 3 and 5 is going to be this probability at 5 minus the probability at 3. So if this is the probability at 5 and this is the probability at 3, so the probability I'm looking for is the difference between the range of the two probabilities. In Excel, this function is called normdist for normal distribution, and its arguments are x, which is the x value here, the mean, the standard deviation, and this parameter at the end, which you set equal to 1, which says you're looking at cumulative probability. So in calculating these intervals on a spreadsheet, this is the way you could do it. Another way you could do it is by looking it up in the table in the back of your textbook and Spiegel's book. Spiegel doesn't, every book gives this in somewhat different form. Spiegel's book doesn't give the integral from -∞, but from 0 to x. So this is in your textbook in Spiegel. And so in this case, we're not looking from -∞, but only on this side up to where we want. So this function is symmetric. If we need to get on the other side, we can add the following half. The total integral is a half on each of the areas out to infinity, because a half plus a half is 1, and total probability is normalized to 1. So you can use these symmetry properties if you have a value less than the mean to calculate the probability. Another way to get these values of these probability functions is from the book that has everything you wanted to know about functions any time. So this is the third method, and this is called the Handbook of Mathematical Functions. This is a good book to own. Maybe, because maybe it's being replaced by computers and stuff, but it's still a nice book. And it's done by Milton, Abramowitz, and Irene Stegun. And this is, I first bought this when the second edition came out from the General Printing Office from the US government in 1964. So I have the hardcover edition of this. And I bought this because it was like on sale when it first came out. And I thought I would never use this book. It's a big, heavy book. And I thought I'd really wasted my money. But I've used this book tremendously. It's been really good. But you're not going to see too many other human beings who have the hardcover edition of this. So everybody else has the edition from Dover, which has got a blue cover, and it's a soft cover. And everybody also has the second edition. I've never seen a copy of the first edition. And the reason why is the first edition has errors in it. In fact, I have a textbook that uses Runge-Kutta fourth order integration, if that means anything to anyone. And there are coefficients in that. And this book on numerical methods has the coefficients wrong, because they were wrong in the first edition of this book. So the first edition of this book has many errors in it. And again, I've never seen the first edition. I've only seen a book that used the first edition and so got the numerical integration wrong. Okay, so the first edition has these errors. And in the second edition, the things that were errors in the first edition are noted by asterisks. And you'll see lots of asterisks in the second edition, which means there were lots of errors in the first edition. But this is a very useful book. Now, a lot of the formulas in this book come from another book, which I'm also the only human being I know who owns. And that's a book which is you're probably not going to buy, but I'll give the name of it and describe a little of the history. But it's called Approximations for Digital Computers. And this is a book by Cecil Hastings Jr. I sort of picture him in a white shirt and a bow tie, but maybe that's my own biases about things. This is published by Princeton University Press in 1955. So you can imagine what kind of digital the computers they're talking about. And the reason why I mention this book is this book has a lot of neat approximations that are useful in doing real-life programming. All of those are contained in this first book, so you really don't need the second book, which describes the theory of how the approximations were made. But the sort of approximations are like this. This function p of x, which is equal to the integral, let's say from 0 to x, of the normal distribution, what they do is they write this as something like this: 1/2 times 1 plus d1 times x plus d2 times x, etc., up to d6 times x raised to the 6th power. So you don't actually have to do the integral or use the computer function to do the integral, but you can write it in terms of a simple algebraic relationship that in this case is accurate to 1 part in 10 to the 7th. And this book, what Cecil did is he gives the magic numbers for all the values of the d's. And so this book has many very simple formulas that are highly accurate and very, therefore, computationally fast to generate things that some person might think you need to do an integral by and some other stuff. And in the 1950s, when people had complicated functions, they looked at errors of the function and how the polynomials could be fit to minimize the errors. So there was a whole theory on how to choose these and these functional forms. And this was desperate because in 1955, computers were somewhat different than they are today. And so it was very difficult to program, and computations are very slow. And so you couldn't do things like an integral. That would have been a tremendously difficult thing to do. One of the things I've been emphasizing in this course is that the mathematics we develop and the tools we have develop very much on our capabilities and our technology and how we approach problems and the mathematical tools we have, or how we approach problems depends very much on the mathematics that we have. And this is an example, another example of that. So in a way, this is very dated because now computers are much faster. But this book has many simple representations of different functions, and they're very useful. And this one is very simple and very efficient to program very fast. So if you need to write a program to calculate integrals of the normal distribution, that's a very efficient way of doing this. It's not so efficient in just calculating the probabilities. If you're trying to do reverse things, for example, pick random numbers that have a normal distribution, this is a very efficient way to do it. So there are lots of interesting aspects in handling this. And in fact, it happens, I just happen to have one of these programs here. So this is a program that I wrote based on Cecil's book and is published in Abramowitz and Stegun on page 932 equation. You can see this is really is a thick book, equation 26-19. And these are the magic numbers. This is a program written in BASIC. I'm trying to learn how to program in C, and I make everyone else in my lab program in C. But I'm really still a BASIC person. But I'm out of the closet on being BASIC. There are a lot of things you can do in BASIC, actually. It's not as bad as you think. And there was once an article in the Journal of the Mathematical Association of America, which is sort of a mathematics journal. And in the article, the guy was describing something, And then he said he had programmed this in BASIC, and there was a footnote on the bottom of the page, and it said, yes, I admit to programming in BASIC. So now the problem is that on the new version of my Macintosh, the BASIC compiler doesn't work, so I'm in a lot of trouble at the moment. So I may actually wind up learning to program in C. But this is a program that actually puts in the total number of measurements and generates the histogram and the probability, and you can see the probability, the area, it multiplies by the number, and gives you, for within each range of the measurement where you put in the mean and the standard deviation, gives you the values you need in the histogram. And I'd be happy to give this code to anyone if they want to reprogram it in C, and then give me a copy of that. But you can see it's just very straightforward. And it has this switch here because, remember, this is going from 0 higher, and if it's less than 0, we have to add that other half. And if we're below the mean, then it does something else. But you can see it's a very straightforward program. So if you ever need to do something like that, I have that. And in the particular case here for the homework, we had the fact that, so again, returning to where we are on this, is that the number of measurements predicted, we'll leave that one alone, predicted by Gaussian distribution is going to be equal to this probability I'm calling capital P times the total number of measurements. And we need to use this z, which is the value of x, which is the edges of the bins, minus the mean divided by sigma. For this particular data set, the mean was 75.25, and the standard deviation, sigma, was 10.375. And this is calculated from the unbiased estimator, which is the sum of xi minus the mean value of x squared divided by n minus 1 square root. I went over last time the derivation of the n minus 1. And for example, if the boundaries of the bin are at 49.5 and at 54.5, then the first z1 value is 49.5 minus 75.25 divided by 10.375, and the second one is 54.5 minus 75.25 divided by 10.375. So this works out to whatever it works out to, doesn't say here. And then what we do is we multiply the total number of values, which in this case was 80 in the data, times this function p at z2 minus p at z1. And in this case, it works out to 1.30. So I can do this procedure for each set of the bins in order to get the number that should be predicted. And I have that worked out here. So this is a whole table where I've done it for the entire problem. These are the experimental values. These are the low and high ends of the bin. These are the amounts that are predicted for each bin. And over here, for me to know where to plot things, I've also plotted the number which is the center of the bin. That little squiggle says center at. There it is, centered. So the center is centered. And so I've made a little plot for myself. And then I can go ahead and plot a histogram that corresponds to the Gaussian fit of the experimental data, and that's actually shown here. So here I haven't printed two bins because they would overlap, so I've printed a triangle that corresponds to the Gaussian fit. So the data here, these of course should be touching, they're not because this is a stupid program in doing the plot, but you can see these are the experimental data, and this is the calculation of the histogram. So as we saw for the person who had the Gaussian fit down here, now things are normalized properly by doing these integrals of the areas. And you can see it's taking me some time to describe this procedure, so it's not trivial. And I think people don't fully understand sometimes. You really need to go through this in order to fit the distribution to the data. So it really does require a little bit of work. And here you can now see that we have this fit. And again, we've done this fit by just taking the mean and variance in the data. Right? We haven't done any least squares fit or minimization or anything, because we proved that theorem that said that if the data has a Gaussian distribution, then the maximum likelihood, the most probable value of the Gaussian, is the one whose parameters are the mean and variance of the distribution. So this has allowed us to do this fit, not by doing the fit for this particular data set, but by having this theorem and then using the results of that theorem to do the fit. So this is how we can compare the histograms. Now, so this is one way of doing it, where what I've done in this way is I've compared the data histogram to the Gaussian histogram. And I can do it the other way too. That is, I can compare the data PDF, I should be able to spell PDF, to the Gaussian PDF. Now again, when I did it in the first time, this is the part that required work, because I needed to translate the Gaussian from the PDF to the histogram. Now if I do it this way, now I'll have to do work on the data in order to translate the data from the histogram to the PDF. So now I'll show you how to do that. So let's do a fresh piece of paper on this. So if we go back to the data, let's say we have a bin in the data between x and x plus delta x. So this is our data bin. And we're going to have the probability density function f of x, which runs through here. Well, first of all, let's notice we're evaluating the probability density function f at really the point x plus delta x over 2. Kind of in the middle of the bin would be a nice place to evaluate it. Sometimes when you do this for different reasons, sometimes you do things at the beginning of the bin, sometimes at the end of the bin. But if we had no other choice, picking the function at the middle of the bin kind of seems like the most intuitive way to do this. And I'm going to call the area of this bin, for reasons that are beyond my understanding, x to x plus delta x, this function m. So m, evaluated from x to x plus delta x, is the total number of measurements in that bin. So the probability of finding an event in this bin is going to be equal to the area of the bin, which is equal to the probability density function x evaluated at x plus delta x over 2 times delta x. Because in this bin, the bin has height f of x plus delta x over 2, and it has width of delta x. So the area is the product of these two. Now, the number of measurements, m, is equal to the probability times the total number of events. So this means that m of x between x and x plus delta x equals f evaluated at x plus delta x over 2 times delta x times the total number of measurements, which we'll call mt. Okay. So this means we can convert each bin into the PDF by dividing through. So the PDF of evaluated at x plus delta x over 2 is equal to the number of events in that bin, m of x, between the number of measurements between x and x plus delta x, divided by the total number of measurements divided by delta x. So this now allows us to convert from the number of measurements into the PDF. But the way we do this conversion is we've got to divide by the total number of measurements, and we need to divide by the bin size. Okay? Now, and so we can do that and get the measurements, and that's done here. Let's see where it's either one or the other. It looks like it's done here. So in this case, these are the centers of the bins. These are the number of measurements. And I've divided each of these bins, number of measurements in each of these bins, by the bin width, which was in this case 5, and the total number of measurements, which is 80. And that's how I generated this set of numbers. Now what I want to compare them to is not the integral of the PDF, but the Gaussian PDF itself. So now it's easy to evaluate the Gaussian. I just do it directly at this bin saw, at this bin center. And in fact, in terms of this Excel spreadsheet, you can see now I've used the function 0, which is not the integral of the PDF, but the Gaussian itself. And I chose A2, which is the center of the bin, times the mean, the functions are the mean and the variance, which is, this is the mean and the variance. So this is the Gaussian evaluated at this point with this mean and this variance, and this says it's the Gaussian. So, and this is the normal distribution function. And then that allows me to get this data. And now I can plot both PDFs. In some way, this is a little simpler than doing all that integral crap that we did before, but it's not so much simpler. In general, people tend to work with histograms because it's more like the data. In a lot of the mathematics of doing this, it's actually simpler to do the PDFs. And then this is a plot that I got out of that. This is actually looks exactly the same, except that the scale is different now because it's not numbers of events, it's really PDF. So I go in tight to show you that it is PDF. And as I said, these were done in the old days, and I thought PDF were lowercase numbers, even though everyone seems to be doing uppercase numbers now. But I have these atavistic tendencies, which are still there. So, and it looks pretty similar to what you saw before, where we have the Gaussian fit and the data. Let me just write down the form. If for some reason you didn't want to use the spreadsheet, if you remember, the form of the PDF was something like f of z equals 1 over the square root of 2 pi e to the minus z squared over 2, where z equals x minus m over sigma. And for some reason, for the moment, I'm not sure why there's not a sigma missing from there. There may be a sigma missing from there, too. So I'm not sure why. Usually there's a sigma there, too. But the way this is normalized, maybe it goes away. So in any case, this is easy to calculate the PDF, which is now uppercase, and compare it to the data. So does anyone have any questions on the fit of the probability density functions or the histograms? Yeah.
How do you measure the goodness of fit, the distribution?
Okay. We're going to do that actually as a homework problem in 2 weeks. So what we're going to do, I'm going to ask you to do a chi-square fit of this data to tell me whether this is a good Gaussian fit or not. And I'm going to discuss that not today, but not next week, but the week afterwards. Assuming I don't get gassed in Israel. The headline on the paper was that they're distributing gas masks. So assuming I make it back, we'll do that in 2 weeks. And the way to do it will be basically to do a chi-square distribution. A chi-square distribution measures how accurately the distribution fits the data. And you'll do that on this data, actually, for this thing, and you'll tell me whether this is a good Gaussian or not.
Is something similar for fractal distribution that you can see how good the
In general, I can't answer that. In general, we can use a chi-square distribution to test the goodness of fit of a distribution. Okay, rather than fitting a function, a distribution we can test by chi-square. Let me just say in passing, for those who are not familiar with chi-square, go back to the Elmo for a second. Thanks. A chi-square involves looking like f predicted minus f observed squared over probably f predicted. And we sum this up over a couple of bins or a couple of points. And then this is the Greek letter chi. These C's are hard in Greek. So this is not chi, this is chi. And then we can look this up, and given the total number of measurements, which are called the degrees of freedom, and from chi-square, we can have the probability that this is a good fit or a not good fit. And this is the way we tell whether distributions are good or not. So this is not like fitting data to points. This is a different problem where we're testing the distribution. In terms of the fractals, we could formally use this to test the fit of the log-log. However, since the fractals have many other non-normalizable properties, I would think that the derivation of chi-square probably has assumed that things are asymptotically normal. And if things are not asymptotically normal, whether the derivation of chi-square is valid or not, I don't know. So that means in principle, I'm not sure whether we can use this to test the goodness of fit of the fractal data. I would say what I would do in a practical sense is I would look at the distribution on a log-log plot. So log PDF versus log X. And I would look at how tight that fit is by some measure, like the correlation coefficient or something. And I would say if that was a good fit, I would say we're probably OK. So that would be sort of a more pragmatic way to handle this. In a formal way, a lot of the mathematics on fitting fractals is not done yet. And one of the points I make in my new book is that, when you have two books, you're allowed to say my new book, is that I think it will be interesting to have that mathematics developed, and a lot of that fitting stuff isn't understood yet. So the real answer is we don't know, and I would just do this seems to me a good, reasonable way to try to handle it. But again, I can't say, since we have non-normalizable distributions, and the chi-square I think assumes asymptotic normalcy, formally I'm not sure the chi-square would work for that. Are there any other questions? Okay, I mean, I think it's worth going through this on the fitting of the Gaussian, because I think it's useful to actually do this in a real-life example and see the Gaussian run through the data. Let me now go over the moments part of the homework. And if anyone hasn't done it, I'll return the homework if your homework isn't complete, and you can finish it and return it to next time, because I think you'll enjoy actually seeing the curve run through the points. I don't know at what level of scale of enjoyment that is, but it's enjoyable. So let me do the next question, which is about the moments. Now, I didn't say, but we can have moments either centered around 0 or the mean. And I didn't say in the homework which one to compute, but actually the moments we would like to compute are the ones centered around the mean. And for most of the work that we do, that's where most of the moments are. So in this case, we had 80 measurements. The mean of the measurements was 75.25. And so the third moment is going to look something like the first measurement minus this mean square cubed, the third measurement, plus the second measurement minus the mean cubed, etc., all the way up to the 80th measurement minus the mean cubed divided by 80. And the fourth moment is going to be the same business raised to the fourth power. So these are the moments centered around the mean. Okay. When we do this, this means that we get that the third moment was 184, which is not 0. Remember, if we had a real absolute Gaussian, if we did the moments around the mean, the third moment for the Gaussian would be 0. So it means it's not quite a Gaussian. And the fourth moment is 27,165. And the second moment, just for fun, is going to be the sum of xi minus the mean squared over n, just by writing it up here. And the variance, the standard deviation, is equal to the square root of this. So it's equal to the square root of the second moment. And so I've just said that the sigma is the square root of m2, or sigma squared is equal to m2. And sigma to the fourth, therefore, is m2 squared. And for a Gaussian distribution, the fourth moment, m4, is equal to 3 times the second moment squared. This is, again, the properties of a Gaussian distribution. So we can test this from the data. From the data, 3 times the second moment squared is 3 times the standard deviation to the fourth power, which is 34,754. So the ratio of 3 sigma to the fourth over m to the fourth, which would be 1 if it's Gaussian, is 1.28 here for our real data. So it's not quite a Gaussian, but it's kind of close. So one way to think of this is kind of like 20% off of a Gaussian in some way. So again, the trick involving these moments are, first of all, I didn't tell you, but I wanted the moments centered around the mean. And second of all, we can see that these relationships for the Gaussian are approximately but not exactly satisfied. And again, I think it's useful to go through this exercise to get a feel of what goes on in real data and how the relationships in the Gaussian are not completely off, but not completely satisfied either. And this shows you that the Gaussian, the data is like a Gaussian, but not completely like a Gaussian. And here I've actually, you can calculate the moments in a number of different ways by using a computer program to keep the running sums. And here I've calculated them by using Excel. I'm not much into spreadsheets, by the way, although I use them a little bit. But I'm just showing you different, since it's obvious to me how to program this, I thought I would show you another way to do it if you don't want to program it. And here I've taken the data and taken each value minus the mean cubed, each value minus the mean to the fourth, and it runs down to the end of page 1, and then surprisingly continues on page 2. Until I come down here to the sums, which I told you were 184 and whatever other number I told you, and the ratio here was 1.28. Okay. So that's the end of the homework. The next homework that we'll do on this data set will involve doing the chi-square. And I have the answer for that in front of me, but maybe I should leave it for your suspense. So it's mixed up here. And as I said, during the break, when the screen goes black and nobody knows what goes on here, I'll return the homework, and people can fix up, if they need to fix up anything, in order to return it to me in 2 weeks. And everyone should really have it done in 2 weeks. It would be nice for everybody to have it all finished at that point. Are there any other questions on the homework or on this fitting? I know when I ask if there are any questions, there are usually no questions. So, because people are trained to answer questions like if it's 53 and next time it's twice as much, what's the answer? But they're not trained to ask, is it really 53, or why are we talking about 53? So, but I ask anyhow because I don't know what's going on. So, yeah. Yeah.
Does it matter when you start making the measurements of the ink spots? Doesn't matter if you start from a specific point, from one side or from the other side.
In terms of
is it going to vary the data?
In terms of where you start on the piece of paper? It depends how you make the ink spots. And the ink spots that I made, it didn't matter. It looks like some people's ink spots were spread out, although they look kind of uniform. They may have been oriented in one direction, but they looked uniform. I don't think it should really matter. My ink spots, there's a bigger clump on one spot and then fewer elsewhere. So that one spot would be, you'd get a different result if you started there than if you started elsewhere. If you had a really fractal distribution, so that as you went to smaller ink spots, there were larger numbers of smaller ink spots, you would get a different result if you started in a different place. But ultimately, the distribution would look the same. So even though there are bigger ink spots in one spot, the relative number of big ones to small ones would still be the same in different spots, even though the absolute sizes would be different. So that is, in terms of a real fractal distribution, if there was a big ink spot and we started here, then everything would be big as opposed to starting here, but so that the means would be different, but the ratio of large to small ones here would still be the same. To say that in a different way, if we did a log-log plot of the probability density function for both of these, log PDF versus log size R, these would have the same slope. I've drawn it exactly wrong. This should be lower. They would have the same slope, but they would start in a different place. And we'll see, since the absolute location here doesn't matter because it's non-normalizable, what's important here is the slope, which is how the relative numbers of big ones and small ones compared. And that's parameterized by something called a fractal dimension. Sorry. Parameterized by something called a fractal dimension. So if things are really fractal, it doesn't matter where you start. This also brings up a very interesting point that we're used to, if we make one set of measurements and make another and characterize them by the mean, we like to think that if the means aren't equal, the measurements are different, or that the system is different. Here the system can be part of the same system, but the means at different times and different measurements in space or different moments in time, if this was a time series, could be very different for a fractal, even though nothing is changing. So how we characterize fractals is different than how we characterize Gaussian distributions. So, but again, I think there's no right or wrong answer from this exercise. It's whatever you get. I've tended, when I do this, to get a very monotonic distribution, but some other people have gotten different distributions or even more Gaussian, depending exactly how they do things. So the point of this exercise is to show that a very simple physical measurement can result in this power law distribution, which violates everything they told you in that other statistics class that you may have had. So and that was the point of the exercise. Okay. Are there any other? Okay. What I wanted to do today is maybe what we'll do is we'll take a when I get started, we have 10:30, 11. No, let's continue a little bit, and then we'll see if yeah.
This pattern applies to structures. Does it also apply to things like how long protein channels will be open and the intervals between the protein channels being opened up?
Yes.
Because those are also fractal.
Yeah. And that's one of the applications that we're using it for. In fact, we see actually mixtures of different types of probability density functions, everything from things that are normalizable that are not fractal to things that are fractal. So I should modify. We see different characteristics in different channels, and sometimes differences between open and closed times. Let me say what I'd like to do now. We'll get started on this, and I'll do the duller part before the break and the more interesting part after the break, when I have more sugar and more caffeine. What I'd like to do is to describe a little bit about how we set up to do experiments. So this is kind of experimental design. And this will deal with some issues that will be important in how we're going to analyze the data. And I'm going to do this really from the perspective of psychology. So this may be useful for people here who are like physicists or mathematicians whose background is not in psychology, to familiarize you with some of the terminology that you'll probably be hearing, if not from me, from other people in the center, or if you go to a psychology seminar or something like that. So I think this will be useful, and it will also raise some issues in how we analyze data and how we set up to do experiments. So let me describe how we do things. Typically, the jargon words that are used in psychology are that we have an independent variable and a dependent variable. Dependent variable. Now, first of all, I think this is bad notation because these words sound too alike and they're very confusing. It's like one should be called independent variable and the other should be called, like, you know, the melon variable or red or something, because these words are too similar. So I think this is a bad choice of words. But there used to be these special relativity paradoxes that we would have in physics courses, and they would always like call these two twins involved, like Tim and Jim, and you could have no idea which one was which. It was like hopeless. So I always like renamed one of these to be a very long name and a very short name. And usually the person with the very long name was the one who was stationary, and the other one was the one that was moving, and then I could tell which was which. So notation in how we call things is important. So I don't think this is such a good notation. But the basic idea is the independent variable is the thing we change in the experiment or control, and the dependent variable is the thing we measure as a result of the change in the independent variable. And typically what we're doing, and where these names come out, is we plot the independent variable on the abscissa and the dependent variable on the ordinate, which normal people would call the x-axis and the y-axis. So we plot the dependent variable here, and we see how the dependent variable changes as a function of the independent variable. So we write the dependent variable as a function of the independent variable. Now, one of the reasons why this notation is not good either is because in mathematics we could always reverse this. We can write some inverse function of the dependent variable is the independent variable, right? If this is a function of that, then we could just reverse that function. And in that sense, this choice of these words is also not good either, because these functional relationships work in both ways. But we're not going to think about it this way. Okay. Now, typically what we do in experiments, and this is something that non-scientists have a very, very hard time understanding, and some scientists have a hard time understanding too, is that we run an experiment, but just doing the experiment alone is not good. We always have to do a comparison to a control. And it is this comparison that's crucial in understanding whether what happened in the experiment is really telling us something or not. And this is essential in doing experiments. Otherwise, it's very easy to fool ourselves. Now, in doing this, the two main types of ways we can handle these in terms of design are called within group and between group experiments. A within group experiment basically means that everybody, all the subjects, get all the independent variables. So for example, we may do an experiment with Fred and Mary where we're looking at the motor effects of alcohol, and we may first of all give people no alcohol, both of them no alcohol, and then later both of them get the alcohol. So both people get both levels of the experimental variable. In the between group design, only one of them, for example, Fred may get the alcohol and Mary doesn't get the alcohol. So in the between group design, we have different people or different subjects get different levels of what's going on in the experiments. Now, the advantages and disadvantages of these two different designs are the disadvantages of the within group design is that if we gave the alcohol first, both Fred and Mary would be wasted, and so then when we have the no alcohol later, we'll get a funny result, right? It won't work right. And this problem is called carryover. Okay. And the way we fix carryover is called counterbalancing. Balancing. These are two jargon words that are used very often in psychology. So these are two good words to know. If you're not into psychology before this, these words, carryover and counterbalancing, are good words to know. And I can give you words for, I like specialize in saving words from different fields. So that is enough jargon for you to like sound intelligent for 10 seconds in some other field. I don't know, did I give you in this class the example of the elevator line? The elevator, if you see someone fixing an elevator, so you see guys fixing, and it can't be like these little elevators here which are pneumatic, but like an elevator in a big building. So this is like a Miami thing. This is not a Boca thing, okay? And it's an elevator that runs on wires, which are not called wires. That's the wrong jargon word. They're called ropes. So what you should ask the guy is you look over his shoulder and say, excuse me, are the ropes on this machine single wrapped or double wrapped over the traction sheaves? And that's got as much elevator jargon as I could put in. So I'll say that again. Are the ropes on this machine single wrapped or double wrapped over the traction sheaves? And that's a really good line. And it's got lots of good stuff in it. And another equivalent example is to go to a molecular biology talk where they're running gels to separate things out on proteins, not DNA gels for sequencing, but protein gels. And at some point, you interrupt the guy sort of after he's been describing the gels for a little while, and you say, excuse me, how do you know the high molecular weight material went into the gel? Because very often things don't dissolve and high molecular weight material is caught at the top of the lanes. And so that's also a good jargon word to know, and that will work. You know, you wait till he shows a couple of gels, and usually he'll say they tried dissolving it with different alcohol or DMSO instead of just water, and they'll say something, but he'll look a little scared, so that always works. And so this carryover and counterbalancing is very much like that. You have to know words like this, and people will say this. So the carryover, again, means that the first condition affects the second one, and counterbalancing it means we scramble the conditions so that we try different possibilities. So for example, we may give Fred the alcohol first and then no alcohol, and Mary we may give no alcohol and then the alcohol. And I'll describe a little bit more detail how we decide how many conditions to use and how we handle this. But this is called counterbalancing in order to beat this problem of the scramble. Now the disadvantages of the between group design, or that, or let me say the advantages of the the advantages of the within group design are that each person or each subject is their own control because they get both conditions or all conditions. Whereas a disadvantage of the between group design, so a disadvantage of the between group design is we're comparing different people. So we're comparing apples and oysters, which is the original quote from Marlowe rather than apples and oranges, actually, if you're into this. So we're comparing different things because here we're comparing Fred and Mary. Maybe Fred and Mary are different. So in a between group design, we have the problem that we're comparing people from different subjects. So the advantage of a within group design is that each subject is its own control. And also we have a smaller number of subjects because we're using everybody twice. Whereas in a between group design, we also need more subjects. Here we have only one person receiving each condition. If we want to have 2 people, now we have 4 here, we still only need 2 people here. So we need more people to run a between group design. So the advantages of a within group design are that each subject is its own control and a smaller number of people. The advantages of the between group advantages are that we have no carryover effects. And the disadvantages are that people are not their own controls anymore. And what we'll do now is take a break until 10:30, and I'll continue these different issues in terms of experimental design and when you get into trouble or not.